So in this video, we want to have want to find some kind of group homomorphism. Sorry, we want to find a subgroup of Z. I mean, so not subgroup. You see, Z adjoin square root of 2. This is not a multiplicative group, okay? Because earlier we found out that, I mean, we didn't find out, but we showed that this is not a multiplicative group, but it is so it is not a multiplicative group, but it might have a subset which is. And so why do we want to find a subset like that? Because if we do find one, for that subset, we can map that subset to another subset, which is a subset of the integers, because the norm maps from Z adjoin n to the integers. And we'll look more closely at which integers that n maps into, because that's actually a very interesting question, right? Because for one, this is actually the Pell equation, right? But does it map? Because for one, we know that there are numbers that map to it. But for example, for 2, we also there are numbers that map to it. But for example, norm of square root of 2, right? What is that? Square root of 2, that is 0 squared plus minus 2 square root of 2 squared minus 4. Yeah, so well, minus 4 has something mapping onto it. But what about for example 2? Is there something that maps onto 2? And I don't know. For me, it's not clear if there is, and we will look more into that. But at the moment, we want to find some subset of this, subset of this that is a multiplicative group. Okay, so what property would it need to have for it to be a multiplicative group? Well, first of all, it would need to have an inverse. So you would need that. That's the only thing we don't have. So we need elements in Z adjoin root 2 such that Z inverse is such that there is a y in Z adjoin. So we need to find all x such that there exists y in Z adjoin root 2 such that x times y is equal to 1. Okay, so because Z2 is a ring, then the numbers that satisfy this are called units in Z. So if a number has a property that there is another number such that their product equals 1, then it's called a unit. So so what we want to do now is we want to, let's call U the set of all units in Z, because, okay, fine, we need to first of all show that the units of Z form a multiplicative group, but this is not very hard, and I'll leave it as an exercise. So what we want to do is we want to restrict the norm to U, and well, where would it map to? So if x was a unit, right, then what is its norm? Well, we see that well, we can take norms on both sides, right? So if we take norms on both sides, we get that n of x, y is equal to n of 1. Norm of 1 is 1. And this is n of x, n of y. Okay, we also see that the norm is 0 if and only if both terms are 0, right? This is true because the square root of 2 is irrational. There is no, you can't find any a minus square root to b squared equals 0. We can't find any a and b that does this unless a and b is 0. So we have that the norm is 0 if and only if any. Okay, so this is one of the properties that actual norm does have. N of x equal to 0 implies x equal to 0. And obviously it's true the other way around. X equal to 0 implies n of norm equals equal to 0. Okay. And so what if the norm is less than 1? Which numbers have norm less than 1? Well, if the norm is less than 1, then it's because norm can only be an integer. If norm is less than 1, then it's 0. Okay. Sorry, the absolute value of the norm is less than 1, then it's equal to 0. So we have that both of these have absolute value greater than or equal to 1, right? That means both of them, we have that either norm of x is equal to plus 1 or is equal to minus 1, right? For x to be unit, if x is an element of the units, implies this is true. Okay. So you see, I don't actually ever give proper proofs. I just kind of give explanations. I don't know if this helps people come up with the proofs themselves or anything like that. But basically, ideas for how you would prove this are here, unless I've made some mistake explaining. But you see that if x is a unit, then its norm is plus or minus 1. Okay, okie doke. So that's going to be it for today's video. In fact, okay, wait, one more thing. The reason we've worked this out is that, so now we know that the ring of units just maps to 1 and minus 1. Okay, and so now, since these are both groups, we have that n is a group homomorphism. Okay, so in the next video we'll see why this is a good, we did this, because now we can actually use theorems we know about group homomorphisms to find out more properties about the solutions of the Pell equation. Okay, so see you in the next video.